So let's finish up our treatment of simple harmonic motion by taking a look at the damped oscillator. In reality, there's always something that's going to be taking energy out of the system. And for instance, if you constructed yourself a pendulum using some small mass tied to a string, if you pull it back and let it go, you notice that the amplitude of its swing decreases with time. And this is mostly due to the air resistance that the pendulum bob is feeling. So I'd like to model damping here by imagining going back to our horizontal oscillator here. But now, in addition to our mass attached to a spring and free to slide back and forth on a frictionless floor, we're going to imagine that this is hooked up to a paddle that is moving through some fluid here. So this combination engineers usually refer to as a dash pot. So we'll say this is a fluid-filled dash pot. To make some analogy, if this was a car, the spring would be literally the leaf spring in the suspension attached to the axle, and the dash pot would be the strut. And the idea is that you literally push a paddle through hydraulic fluid to help dissipate energy so that you don't oscillate too long after you've hit a bump. Now, in reality, the leaf spring is not going to be an ideal spring, and the strut is definitely not an ideal dash pot, but we have to start somewhere. So in this particular case, because of the way this is designed, the drag, instead of being the quadratic drag that we saw for air resistance, is usually more modeled as a linear drag, where the drag force is directly proportional to the velocity, but in the opposite direction of the velocity of the paddle and, for that matter, the mass, since the two are tied together. This B is just a damping coefficient to make everything work out. So if we go ahead and write down Newton's second law of motion for this, F net equals ma, and we'll do this in the x direction. What we'll have is the spring force, which will be minus kx. The drag force will be minus bv. So here, if the object is to the right of equilibrium, it'll feel a restoring force to the left. Here, if the mass is moving to the right, it feels a drag force to the left trying to slow it down. If this is to the left of equilibrium, the restoring force will try to move it to the right. If this is moving to the left, the drag force will be applying force to the right, trying to slow it down. Anyway, this equals ma. All right, so for reasons that have to do with the math of all of this, I'm going to get this into what gets called the standard form. So we can write minus kx minus b. We remember that v is dx dt. And that a is d squared x dt squared. I'll divide this through by m, and then I'll add everything here to move it to the other side. So you'll be left with d squared x dt squared plus b over m d squared x dt plus k over m times x equals 0. And once again, the whole game is we are trying to find some function x of t such that if I substitute it into the differential equation, it all cancels out. Again, you can only do this by guess and check. And here, I'm just going to quote the result and not even bother checking the guess. If you want to check it, knock yourself out. But the position as a function of time can be written as the amplitude times e to the minus bt over 2m times the cosine of omega t plus phi naught. Well, this bit here, the a and the cosine, that looks like the simple harmonic oscillator from before. This exponential seems maybe a little weird, but we'll look at that in a second. The frequency isn't exactly root k over m anymore. It's now root k over m minus b squared over 4m squared. And I promise you, if you crank this through the differential equation, you'll get a mass cancellation out and find that, yes, indeed, this is the function x that satisfies that equation. But this is certainly a mess, and so I'm more interested in talking about this semi-qualitatively. So anyway, it'll turn out that we can describe three regimes of solutions. There's the underdamped regime of solutions. And that'll correspond to where omega is positive. There's the critically damped solution. That will correspond to where omega equals 0. And then finally, there is the overdamped solution. And this is where omega is imaginary. By that I mean it is some number times the square root of -1. Which seems like there wouldn't be a solution, but it actually turns out that there is. So, in the case of being overdamped, being underdamped, if this b squared over 4m squared, the damping term here, is small compared to root k over m, the frequency this oscillates at will be only slightly less than the undamped frequency. This is what we call the lightly damped situation here. But in any event, for the underdamped case, the solutions are always going to plot out to be something like this. So they would be a cosine, except that the maximum value of my cosine is now a function of time. This bit right here is my x max. And then I'm constrained to oscillate within an ever decreasing envelope. So let me plot that out to show what I mean. So here we'll make this the initial amplitude A. This is negative A, like that. And this dashed line here is my x max, which is equal to A e to the minus bt over 2m. Then within that, the actual motion is going to oscillate such that it can never leave this envelope. This is the cosine omega t plus phi naught part, like that. All right, so just like if you swing that pendulum and just let it air damp, with a really keen eye, you'll notice that it keeps oscillating forever. It takes bigger swings, and then those swings decay down, and so forth. We can also go and take a look at the energy. Remember, the energy here, total mechanical energy, is going to be 1/2 k x max, because that's the amplitude at any particular moment, squared. So this is 1/2 k a squared times e to the minus bt over 2m times 2 for the squared. So you just get minus bt over 2m. A lot of times what they'll do is you'll define a thing called the time constant. Tau. This will be m over b in this case. And time constants will show up in other damped oscillating systems, like for instance, if you have an electric circuit with a resistor in it, you can get certain cases where the charges slosh back and forth, but the amplitude of the sloshing depends on is affected by the resistance. Anyway, with this, we can see that the energy as a function of time is whatever you had initially times e to the minus t over tau. So if I plot that out, the total mechanical energy as a function of time, the magic number you want to know for thinking about these things is 37%. What do I mean by that? So this will be a decaying exponential, so this is just the function e of t equals my initial energy, E naught, times e to the minus t over tau. That's one time constant, that's two time constants, three time constants, etc. Now the deal is after one time constant, so if t is equal to tau, this is e to the negative 1, which turns out to be basically 0.37. So we will have fallen off to 37% of our initial energy. After two time constants, because it would be squared, this is where we're going to fall off to 37% of 37% of our initial energy, or 13%. And you can keep that going. At three time constants, we'll have dropped off to 37% of 37% of 37% of our initial energy, and so forth. Again, never strictly hitting zero, but asymptotically approaching it. And for a lot of practical cases, the numbers tossed around are either 3 time constants up to 7 time constants, depending on the fussiness of the system that you're designing when you decide, that's settled down enough. All right. Now, I mentioned the cases of overdamped and critically damped. Now, with these, you would go and look at them and go, wait, if omega is 0, this is just weird. And it is. And you have to you have to actually get the solution for the critically damped case a different way. And then for the overdamped case, where I said that omega is imaginary, you'd think that this would be totally bizarro world, but if you stick an imaginary number into a cosine, it turns into a different function called a hyperbolic cosine. And so it actually winds up giving you a real number back out. I'm not making a big deal of how that works here. I just want to sketch what those regimes look like, and I can draw them both on the same graph. So we'll look at the overdamped and the critically damped cases. So in both of these, Now, if you plot x as a function of time, it doesn't look like a cosine anymore. Both of them will have the same kind of behavior. I'm going to draw the critically damped case in red. Oops. So this is a critically damped case, looks something like that with this asymptotically approaching 0. And then the overdamped case looks like the critically damped case, kind of, except more drawn out. And in both cases, the way you can think of this is it's a balance between the spring and the dash pot. Initially, the disturbance away from equilibrium is large, and so the restoring force from the spring is bigger than the drag force, because when you're out at the maximum stretch, your initial velocity is 0. So initially there's no damping. You speed up because of the force exerted by the spring. Then, as you get closer to equilibrium, the force of the spring drops off, but you're picking up speed, so there's where the dash pot dominates, or the damping, I'll say. So this is the critically damped case. And the black one is the overdamped case. Why does it get called the overdamped case? Well, it's because the damping took over too soon. The spring dominates for a shorter part of the travel before the damping kicks in. So you never got to get as quick a speed as you could before the damping took over from the spring. And so it actually takes longer to return back to equilibrium. Now this becomes a factor when designing suspensions of cars. And if you take a look at the inside the seal where the driver's door closes, you'll see a sticker somewhere. And that the sticker will give the maximum load of the vehicle. Because remember, the overall damping gets determined by b squared over 4m squared here. Also affects this, but divide out 1 power of m. And the main issue here is the damping is sensitive to the mass in comparison to the spring constant. So, as I increase the mass, I will eventually make this number smaller than this number, and I would be underdamped. Now, you don't want underdamped. That's what happens when your struts die. When your struts die, you hit a pothole, and the car just oscillates forever, while because you're just waiting for it to asymptotically approach 0. Ideally, what you would want is to be critically damped, but what you absolutely don't want to tolerate is being overdamped. So the sticker for the maximum weight corresponds to the critically damped case. Anything else, you'll end up being overdamped, but it's better to be overdamped than underdamped, where you hit the pothole and you wind up having to visit the dentist after your teeth rattled too much. So at 0 load, you'll be overdamped, and at the maximum load on the sticker is where you'll be critically damped, roughly, to within whatever jiggle factors the manufacturer decide to put into it. Again, here I'm not particularly interested in the exact functional forms, just because I don't want to get into the weeds of hyperbolic cosines. However, I do want to finish this up by taking a look at what happens if you drive our oscillator. And what do I mean by drive it? Well, for instance, if you're sitting on a swing, which is a pendulum, when you're swinging back and forth, you pull down on the chain, increasing the tension and thus the centripetal force, and you wind up moving a bit as you add energy to the system pumping on the swing. Anyone who's played on a swing set knows that you want to time the pumps so that you're matching how the swing is actually oscillating back and forth. Otherwise, if you just pump the swing at some random time or other, sometimes you're adding energy to the system, sometimes you're taking energy out. It's not as fun. So the damping is always looking to take, so the big moral here is you'll always oscillate at the drive frequency, which may or may not be the resonant frequency, the omega we found before, that is the frequency you want to oscillate at. So I should also say F drive, get rid of that factor 2 pi. So anyway, if we go ahead and plot the amplitude we have as a function of driving frequency, what you'll find is that if the system is heavily damped, so this is our omega, so this is our, well, I guess since I said F drive there, oops. Here, I'm going to leave it as natural frequencies, so I'm applying this as omega drive. If this is omega, the natural frequency that we had before, if you drive it at it and the system is heavily damped, you'll see that the biggest amplitude you get is not that big. On the other hand, if the system is lightly damped, you get a very sharp, very tall peak. Now, sometimes this is desirable, and sometimes it's not. In FM radio receivers, for instance, this is actually how the signal gets encoded. The transmitted frequency shifts back and forth a little bit around what the radio is tuned to, and you move up and down this resonance curve a bit, and that changes the amplitude in the receiver, and that's how you encode the radio wave. So there, being lightly damped isn't necessarily a bad thing. Where it is a bad thing is if you're designing a bridge. Now, the last thing I want is a copyright strike here. So I'm going to ask you, after the video is done, to go and search for the Tacoma Narrows Bridge collapse. So go ahead and take a look for that. What happened here? The Tacoma Narrows was a suspension bridge that went over Puget Sound in Washington State. And this is a case where the civil engineering at the time was still pretty much heavily just built on practical principles developed over the years. How many years? In the case of bridges, a couple of millennia, because the Roman civil engineers who designed bridges were very good at it, and so the first wave of engineering principles that we had for bridge design were built around Roman bridges. Well, Roman bridges were typically looked like something like this, where the bridge deck was a lot of stone and you had a lot of arches and pillars and everything to hold up that load over whatever it was you were going through. Now, as materials improved, so if you jump forward, a couple thousand years, instead of this all being stone, you now say have a asphalt road deck and an I-beam, and you see this over pretty much every interstate. You find that you can now get this reduced down to a less massive bridge deck because you have a steel I-beam and you probably have either 1 or 3 pillars in addition to the anchors. And this is the overpass bridge that you see going down just about any interstate. Now, civil engineers will have a bunch to say about this, of course, but these two bridges have a lot more in common. They actually still have quite a bit in common with each other. The load is being carried through the bridge deck and through the pillars. This is not true for a suspension bridge, which is what the Tacoma Narrows Bridge was. So now with the suspension bridge, you have usually 2 giant towers, and you have a very lightweight bridge deck. It can't even support its own weight usually. And then you have catenary wires that are strung over the bridge deck, like so, sort of. Yeah, it wasn't any better the second time. And you run a whole bunch of wires down these wires. So the bridge deck is actually hanging off of all the support wires attached to the main suspension cables. These suspension cables eventually go into anchors on either side of whatever it is you're trying to cross, basically giant concrete foundations. So you wind up managing a tension load like this, which picks up all the tension in each of these cables, and it's the tension in the cables that's holding up the bridge deck. So unlike the stone bridge or even the I-beam type bridge, the bridge deck doesn't need to support its own weight per se. That's being done by the cables. So that means that you don't have to put nearly as much material into designing the bridge deck. But the over-reliance on the old engineering principles that were based on old Roman stone bridges led the civil engineers who designed this down a very bad path. What they didn't realize at this point is that when you've got something like this bridge here, wind loading isn't really an issue. You've overbuilt the living bejeebers out of it. It's all just a giant pile of stone. It's not really going anywhere. You just overbuilt the heck out of it, and you don't have to worry about the sway too much. You have to worry about a little more here, certainly, especially if you're in a northern state. You have to worry about things like the wind getting funneled underneath the bridge and helping to accelerate ice being formed under the bridge, but that's manageable. This is a different beast. Here, with the likes of the Tacoma Narrows Bridge, you could make the bridge deck so thin that you could barely see it. At that point, that looks pretty much nothing like the bridge deck of a stone bridge. And in fact, looks a heck of a lot more like either a guitar string or an airplane wing. Actually, a combination of the two. So it turns out that, like a guitar string, this will have a bunch of frequencies that it naturally wants to oscillate at. So what was the problem with the Tacoma Narrows Bridge? Well, it's anybody who has competed in the shooting sports will tell you that in most locations on Earth, the wind will have sort of a natural rhythm to it, and you learn to time your shots to go between the in the lulls of the wind gusts, so as to not knock the arrow off course too far. So in the case of the Puget Sound had such a typical frequency. Turned out that that frequency was not too far off of one of the frequencies that the bridge would like to vibrate at. Now I'll leave the details of how exactly it wound up getting driven, because there's a lot of aerodynamics involved and issues of vortex shedding and stuff like that I really don't want to get into. But for our purposes here, the wind gusts were at almost the frequency that, almost one of the frequencies the bridge wanted to oscillate at. So this was actually a fairly lightly damped oscillator, and you're kind of near the resonant frequency of the bridge, the frequency it naturally would want to go at if it were undamped. So that meant that you were, like, say, doing something like this. And basically the instant the bridge was opened, it wound up getting the nickname Galloping Gertie, because people would notice that the bridge deck was swaying while they were riding over it, and it was pretty uncomfortable. Now, the civil engineers who designed this realized that there was a problem, and so they actually set up film cameras all over the place trying to capture the motion so that they could understand it, try to figure out what was happening. Unfortunately, they didn't figure out what was happening soon enough. One day, just because of the change in weather conditions, the frequency of the wind gusts across the Puget Sound changed to match one of the frequencies that the bridge wanted to oscillate at. And so now energy kept getting added by the wind gusts, but not really having any opportunity to come out. So the amplitude of the oscillations was much greater, which you can see if you go and take a look at the videos of this. Unfortunately, that amplitude caused so much stress on the bridge deck that it actually wound up leading to a catastrophic failure of the bridge, and the bridge collapsed. Unfortunately, a dog died. Fortunately, nobody else died in this, so it could have been a lot worse. But it forced a major rethink of how suspension bridges are designed. The Mackinac Bridge was already in the concept stages. This is the bridge that connects the upper and lower peninsulas of Michigan. It was already in the concept stages when this happened. And so anyone who's had the joy of driving over the Mackinac Bridge knows that the center two lanes are an open grating. The reason why it's an open grating is to allow the wind to blow through the bridge deck so as to not push on the bridge deck as hard and hopefully not drive an oscillation. As cars got lighter, this has had the unfortunate incident of having caused a couple of cars to get blown off the bridge. Fortunately, the outer lanes are asphalt, and so if the winds are above a certain speed, they close the center lanes. There's also some underdecking placed on it to cause the bridge to have a zillion different resonant frequencies. The idea being that if anything is driven into resonance, something else is off resonance, and so it will go ahead and pull the energy out of the system. Now, all that to be said, the length of the Mackinac Bridge was different, and the wind frequency of the Straits of Mackinac is way different. So the natural wind gust frequency of the Straits of Mackinac is nowhere near any of the resonant frequencies of the bridge. But in order to gain public approval, that had to be taken into account, and it has in every bridge since. The engineers have learned that they have to pay much more attention to the aerodynamics and the fact that this is now just more like a guitar string than it is a piece of stone when modeling bridges, when designing bridges. All right, so that will do it for our treatment of simple harmonic motion. We'll catch you in the next one.